2.2 is all about inverses of a matrix. So a matrix that is not invertible, that means it does not have an inverse, is sometimes called a singular matrix. If A is invertible, then the solution to AX equals B is, yes, A inverse times B. And A is invertible if the determinant of A is not 0. The little arrow above B, what? Oh, yes, yeah. So I have a matrix A, 1, 4, 1, 6. I'm going to find its inverse in 2 different ways and check that it's actually an inverse. So for a 2 by 2, I have a special formula for finding the inverse, right? So I know that if A is the matrix A, B, C, D, then A inverse is 1 over AD minus BC times A, like rearranged a little bit. So A and D swap, and B and C stay where they are, but they become opposites. So that's my formula for an inverse matrix for a 2 by 2. 3 by 3, I mean, it has a formula, but it's so unwieldy that like we don't memorize it. But the 2 by 2 one is really nice. And then for anything larger than 2 by 2, we have another method that I'll show you after we do this. All right, so in this case, A inverse is going to be 1 over A times D, 1 times 6, minus B times C, 4 times 1. AD minus BC. And then times the matrix A, but rearranged a little bit. The 1 and the 6 are going to swap places. 4 and the 1 stay where they are, but they become negative. And then I just simplify this. So 1 times 6 minus 1 times 4, that's 2. So this is a half times 6, negative 4, negative 1, 1. When you multiply a matrix times a scalar, you just multiply every entry in the matrix by the scalar. So this becomes 3, negative 2, negative a half, a half. So there's my, using my formula to find the inverse. I'm going to show you another way to find the inverse using your calculator and RREF. And then once we verify that it comes out the same both ways, I'm going to use the definition of an inverse to verify. All right, so my calculator method takes A and augments with the identity, and then you row reduce, and the identity will land over here, and A inverse will land on the right once you row reduce. If you don't get the identity here on the left, that means that the A inverse doesn't exist and that there is no inverse. So I'll have my calculator do this. So I'll go into matrix. So A is a 2 by 2, which means when I augment with the identity matrix, that's also going to be a 2 by 2. So it's going to be 2 by 4. So here in the first 2 by 2, the first 2 columns of my 2 by 4, I'm going to put A. So I have 1, 4, 1, 6. So I have A there, and then in my next 2 entries, I'm going to put the identity matrix for a 2 by 2, which is 1, 0, 0, 1. So quit out of there, and then I'm just going to RREF that. So I go second matrix, math, go down to RREF, and choose matrix A. So I have the identity moves to the left, and I have 3, -2, -1/2, which is what I got using the formula. All right, so that's the method you would use if you also were trying to find the inverse of a 3x3 or a 4x4, anything larger than 2x2, you'd do that. You put A on the left, the identity for that size matrix on the right, and then row reduce and they'll swap. You get the identity on the left, A inverse on the right, and again, if you don't get the identity on the left, if you get anything other than the identity, you just say, okay, that means A inverse doesn't exist. All right, so I want to verify that I have the inverse. So I just need to check that A times A inverse is supposed to give me what? The identity. That's the definition of an inverse. So if you think about real numbers, like multiplication of real numbers, the identity element is 1, because 1 times anything gives you that thing back. So in our case of matrices, the identity element is 1, 0, 0, 1, because when you multiply that times any other matrix, you get the matrix. So in real numbers, matrix multiplication, multiplicative inverses would be like 5 and 1/5, because 5 times 1/5 gives you the identity element of 1. So that's the same idea with matrices. I want to make sure that when I multiply them, I get the identity element. All right, so A is 3, -2, -1/2. Multiply that by the A inverse I found. Oops, sorry, that was A inverse. Start with A. 1, 1, 4, 6 times A inverse. 3, -2, -1/2. And I should get the identity. So 1 times 3 plus 4 times -1/2. That's 3 plus 1. Sorry, it's 3 minus 2 is 1. So that was 1, 4 times 3, -1/2. Then I'm going to do 1, 4 times -2/2. So 1 times -2 is -2. 4 times 1/2 is 2. Add them together and you get 0. And then you get 0, 1 when you do the next one. So check. Reverse the order should give you the same thing, right? If you also do A inverse times A, you should also get the identity. All right, so the benefit of having the inverse is that you can use it to solve an equation. Just like if I was trying to solve like 5x equals 10, right? To undo that, usually we think divide by 5, but really we're doing the multiplicative inverse, which would be multiplying by 1/5. Multiply both sides by 1/5 to get the x by itself. So if I have ax equals b, I can multiply, I want to get the x by itself because I'm trying to solve that. I can multiply both sides of that equation by A inverse. A inverse times A times x equals A inverse times B. The A inverse and the A cancel to give you the identity. So you just have x equals A inverse B. So if I'm trying to solve ax equals b, where b is 1, 2, then I can just say, oh, well, that means that x is A inverse, which I calculated to be 3, -2, -1/2, multiplied by b, 1, 2. So my result should be a 2 by 1 vector. 3 times 1 plus -2 times 2, and -1/2 times 1 plus 1/2 times 2. And so we have 3 minus 4 is -1, and that's -1/2 plus 1 is 1/2. And then we're supposed to confirm by row reducing on the TI. So I'm just going to pull up my calculator. and go into matrix, edit matrix A so that it's A augmented with a 1, 2. So I'm going to make sure I get the same result using our old method. So it's going to be 2 by 3. So A is 1, 4, 1, 6, and then I'm augmenting with 1, 2. Oops. It's supposed to be a 1. Okay. And then matrix, math, REF. So I get -1/2 is my result. So same thing I got using A inverse. Yep.
Is the inverse?
Yes. Yep. All right. So A, B, and C, invertible n by n matrices. So they're square matrices. And I can now use my knowledge of inverses to solve an equation that has matrices in it. So A times B plus CX equals C. I'm trying to solve for X. That is, get X by itself. So what do you want to do first? You can use the rules of matrix arithmetic. You can use inverses. Goal, get X by itself. Use regular arithmetic. So what would your... Yeah, just move stuff around to get X by itself. I can think of 2 steps I could do first, right? I could distribute the A, because distribution works for matrices. Or I could, if those were all numbers, I would divide by A. You can't divide in matrix land, but I could multiply both sides of the equation by A inverse to move the A to the other side. Any preferences? Do the A inverse? Okay. So I'm going to multiply both sides of my equation by A inverse so that I have A inverse A times B plus CX. And you'll notice I'm on the left side, I multiplied by A inverse on the left. Because matrix multiplication isn't commutative, you have to do the order the same on both sides. So my right side of my equation has to have the A inverse multiplied on the left. All right, so my A inverse and my A cancel on the left, so I just have B plus CX equals A inverse C. So if I want to get the B, remove the B, can I just subtract it? Matrix, is subtraction defined for matrices? Yeah, you can. So I'm just going to subtract the B. So those go away, and so I have CX equals A inverse C minus B. And then how do I get that C off of my X to get the X by itself? Say that again. So if those were numbers, yeah, I would divide both sides by C, but because they're matrices, there is no such thing as division in matrix land. So instead, I'm going to multiply by the inverse of C. Yeah. So you're just, it's really hard to force your brain to leave real number arithmetic. You just have to keep reminding yourself it's different. So when you say the inverse of 5, even when you write like our notation even means, right? That means the inverse of 5, right? 5 to the -1 means 1/5 in real numbers. Our notation reinforces the idea of inverses as multiplicative inverses. But when I write A inverse, if A is a matrix, that doesn't mean 1 over A, right? It's a different notation. It just means the multiplicative inverse. So I'm going to multiply both sides of this equation by C inverse on the left. So I have C inverse CX equals C inverse times A inverse C minus B. So I have to multiply the whole right side by C inverse, so I put some parentheses in there. So my C inverse times C, those cancel. And remember, they have to be right next to each other in order to make them cancel. If I had multiplied both sides by C inverse on the right, like that, then they wouldn't cancel because you can't change the order of the X and the C inverse because it's not commutative. So I had to put it on the left. Oops. What did I do? Hold on. Yeah, the commuted, it still is not commutative. You have to hold the order when you distribute. Oh, come on. There we go. Okay, so my C inverse and C cancel, so I just have X on the left. And then on the right, when I distribute that C in, it has to go on the left of everything when I multiply it in. So I'm going to have C inverse AC minus C inverse B. And I can't cancel that C inverse and that C because they have to be touching because I can't change the order. Oh, nope. I just missed the inverse. Yeah. C inverse A inverse C minus C inverse B. So that's as far as I can go. Now X, what is it? Is it a vector? Is it a matrix? Is it a number? It's a matrix. Yep. Yep. Because it's equal to a bunch of matrices with stuff being done to it, right? So all of my original matrices, A, B, and C, were n by n. That was given. They were square matrices that are n by n. So if you take the inverse of an n by n, it's an n by n. So this is an n by n times an n by n times an n by n minus an n by n times an n by n. So when you multiply an n by n times an n by n, the inner dimensions match, the outer dimensions are the answer, so you get an n by n. So these three multiplied together give you an n by n. These two multiplied together give you an n by n. And when you subtract matrices, you just subtract component-wise, so the result would still be n by n. Okay, so it is a matrix, and it's an n by n